Welcome, my friends! Consider the expression the square root of 5 times the square root of 10 minus 3 times the square root of 7, which we would like to simplify. We can distribute the square root of 5 to get the square root of 5 times the square root of 10 plus the square root of 5 times negative 3 times the square root of 7. Recall that one of the properties of square roots is that if two square roots are multiplied, then you can multiply their insides together. So this could be rewritten as the square root of 5 times 10 minus 3 times the square root of 5 times 7. This simplifies to the square root of 50 minus 3 times the square root of 35. Now we think about perfect squares that the inside of our square roots can be broken into. We can rewrite the square root of 50 as the square root of 25 times 2. But the square root of 35 does not have any perfect squares it can be broken up into. Simplifying, the square root of 25 is 5, so we have 5 square root 2 minus 3 square root 35. Since our two terms have different square roots on them, we cannot combine them, so this is our final answer. Let's try the square root of 15z to the third times the square root of 3z. Since we have two square roots multiplied together, we can multiply their insides. We have the square root of 15z to the third times 3z, which simplifies to the square root of 45z to the fourth. We can rewrite this as the square root of 9 times 5 times z to the fourth. 9 and z to the fourth are both perfect squares. The square root of 9 is 3, and the square root of z to the fourth is z squared, so that our final answer is 3z squared times the square root of 5, as the square root of 5 is not a perfect square and cannot be simplified. Let's try some square roots with fractions. We have the square root of 125 divided by 80, which we would like to simplify. Now, you'll want to simplify the fraction underneath the square root first if you can. In this case, both the numerator and denominator are divisible by 5. 125 divided by 5 is 25, and 80 divided by 5 is 16. We have the square root of 25 divided by 16. One of the properties of square roots is that you can rewrite a quotient of one square root as the quotient of two separate square roots. So this can be rewritten as the square root of 25 divided by the square root of 16. Now it should be clear that this simplifies to 5 over 4, which is our final answer. Let's try another one. We have the square root of 5 divided by the square root of 80. This one is written as two separate square roots, but it might be useful to rewrite it as one single square root of the square root of 5 over 80 to allow us to reduce our fraction. Both numerator and denominator are divisible by 5, so this can be simplified as the square root of 1 over 16. Now we can break this back into two separate square roots to get the square root of 1 divided by the square root of 16. The square root of 1 is just 1, and the square root of 16 is 4, so our final answer is 1 over 4. Okay, let's try something a bit different. You might remember that the square root of x is just the same thing as x to the 1/2 power. This applies to higher roots as well, so the cube root of x is equal to x to the 1/3 power, and the fourth root of x is equal to x to the 1/4 power, etc., etc. Well, if what you have underneath the radical sign is already raised to a power, like the fifth root of x squared, this can be rewritten as x to the 2/5 power. This should hopefully make sense. If we had just x to the first power, the answer would be x to the 1/5 power. So if you have x squared, or x to some higher power, the exponential form will just be x to whatever that power is, divided by the number on the root. We can also go the other way around. So if you have x to the 4/7 power, for example, you know the denominator corresponds to the root, so we have the 7th root. Underneath the radical sign, we have x to the 4th power. If you're someone who likes formulas, you can think of x to the m over n power as equaling the nth root of x to the m power. The denominator of the fraction always corresponds to the root, and the numerator corresponds to the power on the variable. Alright, let's move on to equations involving square roots. Say we have the square root of x minus 13 is equal to negative 15. The way to cancel out a square root is to square both sides, which gives us x minus 13 is equal to 225. If we add 13 to both sides, we get x is equal to 238, which is our final answer, right? Well, actually no. Try plugging in 238 into our original equation. We get the square root of 238 minus 13, which is the square root of 225, which equals positive 15, not negative 15. So why didn't it work? Well, when we squared both sides of the equation to clear out this square root, there's actually an inherent assumption that whatever is on the other side of your equation is positive. Think about it. Both 15 squared and negative 15 squared equal 225. You might remember that square roots can't even be negative in the first place, so there was no way this equation was ever going to be true. The square root of x minus 13 will never equal negative 15, or any negative number for that matter. Therefore, there is no solution to this equation. Bonus term for you here. The solution of x equals 238 is not a real solution, but rather we call it an extraneous solution. Let's try another one. We have 1 equals the square root of 3x minus 15 minus 2. We want to have the square root isolated on one side of the equation before we square both sides. So first we must add 2 to both sides. We have 3 is equal to the square root of 3x minus 15. We are at the point where we need to square both sides of the equation, but we have to ask ourselves, does it really make sense to square both sides, or is there no solution? Well, this time we have the square root of something equaling a positive number, positive 3. So there should be a solution to this one. We only run into an issue when the square root of some number is said to equal a negative number. Squaring both sides, we get 9 is equal to 3x minus 15. Adding 15 to both sides, we get 24 is equal to 3x. Dividing each side by 3, we get x is equal to 8. We don't really have to worry about 8 being an extraneous solution because we checked before we squared each side that the square root equaled a positive number. But if you want to check anyways, we have 1 is equal to the square root of 3 times 8 minus 15 minus 2, which simplifies to 1 is equal to the square root of 24 minus 15 minus 2. Or 1 is equal to the square root of 9 minus 2. Or 1 is equal to 3 minus 2, which is 1 equals 1. Which verifies that our solution is correct. Let's try one last problem. We have the square root of 3x plus 14 minus the square root of x plus 6 is equal to 0. In this case, we have two separate square roots. We want them to be on opposite sides of the equation before we square them, so we add the negative square root over to the other side. We get the square root of 3x plus 14 is equal to the square root of x plus 6. Now we can square both sides, but you might be wondering if we will have extraneous solutions. Well, since the square root is always positive, both sides of the equation are positive. We don't have the situation where the square root is equal to a negative number, so we don't really have to worry about extraneous solutions here. If you aren't sure, you can always check your answer at the end. But in this case, we don't need to worry. Squaring both sides, we get 3x plus 14 is equal to x plus 6. Subtracting x from each side and subtracting 14 from each side, we get 2x is equal to negative 8. Dividing each side by 2, we get x is equal to negative 4. If you wanted to, you could plug in x equals negative 4 into both sides of the equation. We have the square root of 3 times negative 4 plus 14 minus the square root of negative 4 plus 6 equals 0. This simplifies to the square root of negative 12 plus 14 minus the square root of 2 equals 0. Or just the square root of 2 minus the square root of 2 is equal to 0, which is just 0 equals 0, verifying that x equals negative 4 is the correct answer. Alright my friends, that finishes our discussion of square roots.